Boy, oh boy, oh boy. I do wonder if I could do this. Browser? Browser! Oh, that's not right. Okay. Okay. I guess that's the chat. Let me put that over there. Luigi! Browser! Let's go. I love that video of speed. It's one of the funniest things I've ever seen. The LGBTQ? Okay. Welcome, people. I guess it's just Luigi, but that's okay. We're doing some CAD, as per usual. I'm going to pop this out so I can see it. And we're going to bring up diffusion. Except, I guess I can't see pop-out windows, so we're going to put it over here. Maybe that'll work. Okay, I guess I can see it. Hopefully it updates. Okay, folks. No, I don't want you to see my YouTube recommendations. What am I talking about? Get out of here. Get out of here. Let's see, is the live working? Looks like it's working. Cool. No clue if anybody is watching. Probably not. But we are going to be doing something here because I got a little CAD to do. So I thought, why not, you know, show it live, do it live. Okay. I donated blood yesterday. So I'm very dehydrated. They said no caffeine for 24 hours, and it's currently been 30 hours, and I still am pretty dehydrated. So I'm going to keep that going. I don't drink a lot of water anyway. Definitely have to get better at that. So here's the dealio. We have a... Thanks, Luigi. Luigi is watching. Luigi always watches. 22 farad capacitor. Sorry, 2200 microfarad capacitor. And this is going to be the key to solving all my issues. We have separated this module, if you've seen so far, into mechanical, electrical, and power, being the battery. But the battery requires some heavy filtering, which will be explained in a later video. But I think this 2200 microfarad capacitor will do it alongside a 1 ohm resistor. Now, I'm just trying to model this here. I have the urge to explain to you guys the science, but I already filmed all of that, and that's going to appear in the video. So I really just want to make space for this capacitor in this power pack, which is a big, bulky capacitor. I need to figure out how that's going to work. First things first is I already know that I need to expand some of these wire spaces here. I feel like I can sneak it in there somehow. You know what I mean? It just like barely fits. I feel like where there's a will, there's a way. And I'm Will, so there must be a way. All right. Hope everybody who's watching is having a good day so far. It's the middle of a day. Well, I guess for those of you folks in school, school's probably out soon, I'm guessing. On the East Coast, that is. Okay. probably need a little more, something like that. I might do it. No, you know what? Gotta be more. Gotta be more than that. 0.2. That's what we need. All right. And we're going to try to do this efficiently. So I'm going to move this back here, make it 12.2, make a new body. Move that new body. One from here to, oh, we got to make a copy to here. Great. Okay. And I want to show the cover so that I can cut both at the same time. The battery holder is somewhere. It's not that. Back cover, not that. Where is it? Is this still a body? No. This is what I get for not touching this CAD file in like 2 weeks. This one? Nope. Not that one. Not that one. This one. It's got to be this one. Booyah. Okay. Great. And so now we can take target body, tool bodies to be this one and this one. Boom. We kept the tools, right? Did we not keep the tools? Keep tools. Okay. Great. And now we cut this one too. This one, this one, and this one. All right. So now the wires will have an easier time. That's good at least. Gotta solve all the problems. So now, let me make this capacitor. 22 farad, 22, what am I saying? 22 microfarad capacitor. Starting at 12.7 millimeters in diameter and 20.4 millimeters in height. So we're going to use this plane here. And so 12.7, we'll make it 12.95 for tolerance's sake. All right. And what was it? 20.6. 20.9. So there's that capacitor. And it could fit. We've got a button to deal with, that's for sure. Oh, do I still have that thing here? Don't believe so. But I also, wait a minute. No, there's one. So this button stretches down. Four millimeters, to call it 5. Okay. That's 5 millimeters under here. 5 millimeters. Okay, perfect. And then what do we got? Okay, just leave that plane there. So you can see a lot of space being taken up here. But let me just move this capacitor. Yes, hello. I would like to move it. Thank you. I like to move it, move it. I like to move it, move it. I like to move it, move it. I like to move it. Okay. Whew. Okay, so something like this could probably work. See how that looks. He's a big boy. He is a big boy. Don't forget we need space for the wires too. I'm gonna let's see here. Okay, honestly, like this, maybe. How thick is this? That could maybe, I know it's getting in the way of the screw hole, but I could move it a little further probably. Could move it just a bit further. So it's just out of the way of that screw. Okay, but now it's interfering with those wires. It's always tricky to fit something so big in something you need to stay small. But I'm determined to not increase the size of this thing any more than it already is increased. And I'll consider it a W if I can keep it this way. Interesting, very interesting. I'm concerned. I don't know. I don't know if this is possible. So Buigi has asked what the problem with the device is. And essentially it's this. Even though I'm using a battery that is well within the range of the voltage and current, well, just voltage requirements of the motor driver, and the motor isn't drawing any more current than the current driver allows, the motor driver is burning out. And I've realized the reason for this is that when you have a motor, it basically is a resistor and an inductor. And when you have a battery, it's a constant DC voltage source, but it also acts a little bit like a capacitor, and it has its own internal resistance as well. So all of those factors together basically mean that you get an RLC circuit effectively. And RLC circuits can generate oscillations. When the motor first turns on, current starts flowing into it, and a lot of current, because this device requires a lot of torque from the motor to charge that massive spring. And so what ends up happening is there's like this ringing back and forth that happens in the circuit. And on the side of the battery, before the motor driver, that ringing presents itself as an oscillation with very high amplitude that surrounds 9 volts, but the peak of it is more like 12 volts, and the valley of it is more like 7 volts. And these motor drivers are only rated for 10 volts. Even though it's probably a little bit of a safety factor there, this is enough for the device to immediately burn out. And it's not good, so we want to try to prevent that. The thing is, I need a really, really big capacitor to do that, because you've got to filter out really low frequency oscillations as well, not just the higher frequency oscillations. So if we can fit the capacitor in this device and hopefully fit the resistor in the device too, that 1 ohm resistor for a little bit of damping, then we prevent the motor driver from burning out in a situation that it should totally be able to handle. So that's all. That's all. But fitting this mechanically is going to be tricky, it seems. Oh, no. I don't know what that was. I really need a... Yeah, I need a section analysis here. Gosh, my mouth is so dry because of this stupid blood donation. Not stupid. Excuse me. Not stupid. You should donate blood. You should definitely donate blood. It's actually a lot of fun. You know, you go there, everybody's very nice. I also realized that I could donate platelets. And if you donate platelets, then you get to sit there for 2 hours with a needle in your arm, which does not sound fun, but they'll like bring you food and you get to watch something. I don't know. I don't know if it's worth the 2 hours with a needle in your arm, to be honest. Those, but it is very beneficial for cancer patients, that's for sure. So we need this capacitor to fit under this plane and to the right, sorry, to the left of this plane. So that gives us two tangents on which to place this capacitor, at least, right? What do we got? What do we got here? This is a plane. We have to, real quick, not show construction, add a new plane, re-show construction, and then boom. So now, if I just take a look at this here. What is up, Arene? We are trying to fit a giant capacitor in a small space. That's what we're trying to do. We've got to modify the power module of this wrist-mounted grappling hook so that we can fit a massive capacitor inside. And that's what this cylinder is, massive capacitor. Okay, I want to make sure. Is that this? I guess so. So I don't know, maybe. I don't know. I feel like you're probably thinking of someone else, to be honest, given your enthusiasm. But what I will eventually make will probably be better than what that guy made. So just stick around and see. So this needs to be tangent to these two. Okay, bro. Well, very kind, very kind. Let's see here. So that's tangent to both of those planes there, um, which is good. But if I look at what the whole thing looks like, yeah, that's right. I eyeballed the gasket between the metal parts, but then I didn't because it was better to use the mathematical approach and do calculations based on the elasticity and all that stuff. Yeah, that's me. Welcome back. Okay, let's see. This is I'm just worried this is not, well, could fit still. Could still fit. Possibly. We're gonna have to make some serious alterations, that's for sure. So basically, gosh, why does this have to be so massive? Let's see here. This sucks. I hate it when I have to add something like this and it just does not fit with what I already have. Because that means a lot more work. Trying to see here. Oh, you're trying to get into engineering yourself. Talk to me. What do you want to do? What kind of engineering? I always love to hear stuff like this from people. Nice. ECE. ECE is one of the coolest departments at any university, I feel like. I feel like they are just smart. I don't know. I had a guy, one of my close friends was in computer engineering. And I feel like in computer engineering and in electrical engineering, and surprisingly not so much computer science, they get like really heavy mathematical education, such that I was when this guy was in his master's and I was in my PhD program, he took a robotic kinematics and dynamics class with me, which is very, in my opinion, like mechanical class because it deals with like uh, transformations and geometries and that sort of thing. Um, but there's also a controls aspect, but there's just like a lot of like partial differential equations because you're dealing with Lagrange, I think. Someone told me I pronounced this wrong recently, and I've I don't know what's correct anymore. I think it's Lagrange is correct. Um, uh, you know, uh, Lagrangian dynamics. I used to say Lagrangian. I think is wrong. Um, Lagrangian dynamics, and so you're dealing with that. So Lagrangian, Hamiltonian, that sort of stuff. Partial differential equations. Difficult math, in my opinion. I mean, kind of elegant, but still, kind of, out there. Especially, there are a lot of proofs in that class. Basically, what I'm getting to is difficult class mathematically. In my opinion, more of like a mechanical oriented class. This guy comes from computer engineering, comes in, understands the subject material. He's not a roboticist, understands the subject material like that. He was teaching me. I was like, he's an intelligent fella, and he works for Apple now, and I do this. So yeah. No, the capacitor is not the main source of power. You'll see here there is a 9-volt battery here. But the problem that I've explained to people who were here before is that there are like weird voltage dynamics that happen when you have uh, uh, a battery and a motor. That's as much as I can really say. When you have a battery and a motor, it seems super simple, right? But if the motor requires a lot of current and that like immediately flows into the motor, the circuit that is formed by the battery and the motor and the switching controller causes some oscillations that can just burn out the motor. And those oscillations, not burn out the motor, sorry, burn out the motor driver. But I think like I need a really, really big capacitor to damp out those oscillations. Otherwise, I'm going to be dealing with this forever. So this is the first time I've ever actually used a capacitor in this sort of like medium range. I've used small capacitors to damp out high frequency oscillations. And I've used really big capacitors with high voltage ratings to store a lot of power that I could discharge into like a taser or a coil gun, or I've experimented with discharging that into other things like solenoids to get like an instantaneous high amount of force from them. That's always fun. But this sort of like mid-range, it's this 2200 microfarad 16-volt capacitor. It's like the first time I've ever really used anything like that, and I've only seen them on like if I've like opened up a power supply and that sort of thing. But apparently, and according, I've done the simulations too. I'm not going to show it now, but the circuit that I simulated here, it only works if I have this a really high capacitance here. So yeah. Oh, no. What you doing? Stop that. Okay. Get rid of that body because I really am annoyed by that. So let's see here. By the way, let me ask you a question, because you referenced a video that I posted in June, and I've basically been posting every 2 weeks since then. Like, I just like am so annoyed by the lack of impressions that YouTube seems to grant me, or the lack of consistency in people who like see one of my videos and are like, "Oh, this is awesome," and then don't come back, even though I post all the time. It's just interesting. But I'm not gonna get too hung up on that right now. I've got a job to do. Like this hole is there, and these wires are here, and it's just a little bit too long, and that's like, oh my god, that's so annoying. I think I'm gonna have to get rid of this hole. You know what? I can move this hole. That's probably a good way to do it. Hey, 610 is here. I'm glad you've recovered, 610. I'm glad you're back in the semester. That's very good. That couldn't have been easy. That's for sure. All right, we're going to place this here is what we're going to do. You let me know if you need any help with tutoring or anything. Happy to oblige. Thanks, 610. I love people who dig deep. Those people are my friends. Yeah. Go to sleep. Have fun being on the other side of the earth. Come back soon. We'd love to have you. Bye-bye. All right. Hopefully it treats me well. I really hope so. 610 got robotic vision. Nice. Probably just like computer vision, I guess. Mobile robots, mechatronics lab, intro to mechatronics. 610, you are getting to the stuff where my expertise won't be as good, but mechatronics, that is my expertise. Mobile robots and robotic vision, I think you got to defer to your TA. Not me, TA, your TA. But mechatronics lab and intro to mechatronics, that I can certainly help you with. Yeah. Sounds like a fun hobby. Okay, so I close that hole over here. And the cover right here. Let's check that out because we no longer have this hole. So we've got to get rid of that too. If this is truly parallel. Hello, Onyx. Welcome, welcome. By the way, Happy New Year to everybody. It's sort of the first time I'm seeing all of you in this new year. 610, you will always be one of my most ardent supporters, and for that, I am grateful. I'm glad that some people see what's going on here. Mashin says, hey, oh, mesh is retracted. Well, it seemed like a nice message in the meantime. All right, we're not going to put that hole back until we know that the capacitor can fit. That's what we're going to do. Mashin, hey, just want to express my support and admiration. Was following you from 2015, and I think and progress you made during this time, just amazing. Wish everything work out well for you. Thank you, Mashin. That's very kind of you. And it's good to know that I've got people who've been watching me for such a long time because I've been here, you know. Interesting. Home remedy to take the yellow may be gone. That's good. Gotta, stay talking to your doctor. They know best. They know best. I may be a doctor, but I'm not a doctor of medicine. Do love grapefruits, though. Unisolate. Okay. So this capacitor is invisible, and that means it can fit. That means it can fit. And I think we can make it fit. I believe. Do you believe? Does everyone believe? It looks like it can fit. This is big news. Let's just see if it interferes with anything else, if not that hole that was there before. Honest beliefs too. Okay, so it looks like it doesn't interfere with anything except this like wire track here, but I'm just gonna go ahead and cut and we can deal with that afterwards. So this one, keep tools. The gag was playing the part that you like fruits in the background. Interesting. I assume you mean my graduation ceremony. I'm not quite sure. It was a fun ceremony. What always kind of irks me, and I suppose I did this to myself. Um, so performance decrease, you probably get, you know, a bit of performance decrease. However, what I'm really going for here is compactness and accessibility. So these 9-volt batteries, they're not the best for this application. I'd much rather use the 3S pack, but I really think that this is a better solution for this particular project. Now, I haven't developed the circuitry for internally charging a 3S project. I love using 3Ss for research, right? But now we're getting to like production stage, or like consumer facing stuff. Now that is to say, I wouldn't dream of using your ordinary 9-volt battery. I've got these guys here, and these are 9-volt batteries with supposedly 1,300 milliwatt hours. Now, I don't really believe that, but these are LiPo 9 volts. But what's really inside here is, at least I think, is just a single 3.7 volt LiPo 1S with a step up. And it has a USB-C charge in the back. Now, I think that, I don't know. I don't know how long this is actually going to last. I'm willing to try it out. But this actually also leads to some of the issues and why I'm adding this capacitor, because this, having an internal voltage regulator, it doesn't have as much of an internal resistance. And the problem with that is the resistor acts like a damper for some of these oscillations. At the very least, it lowers the sort of set point of the oscillations because there's a voltage drop across the internal resistance. So when I use a typical 9-volt with the circuits that I've designed, it works, but not really well, even though when I hook it up to my power supply 9 volts, it should work really well. And so it kind of acts like it has a lower voltage than it actually does, because the internal resistance of these alkaline batteries is high and drops the voltage as a lot of current flows through. With these guys, I don't have that problem, but I still get the ringing from the RLC circuit that's formed with the motors, and it burns out the motor driver. And so we can't have that either. So this giant capacitor will allow me to use these better 9-volt batteries, compact USB-C chargeable. I don't know. I'm hopeful. I'm hopeful at the very least. That's where I'm at. Okay, so that's that. Keep tools there. And one more. Just one more. Tool bodies. No. That's opposite. Target body, cover, tool body, capacitor. Yeah, I have a balance charger, right? But like when you have a LiPo, you really want to use a balance charger. And that's something that I haven't really figured out how to work that into like consumer product yet. Yeah, because you would need to. I'm not a battery expert. I haven't made any battery management devices. I only use them, you know, and so for me, it's about doing what's most accessible and the cheapest possible solution, so that I'm not selling these for $1,000. Oh, that's cool. 610 is practicing handstanding. I love handstanding. Handstanding is great. Definitely keep up with it. And soon you can do handstand push-ups. That's right. That'll be fun. I recently got to go to a parkour gym for the first time in like 2 years, I think, which I've been doing parkour just outside. And this gym burned down 2 years ago. It was my go-to. So okay. So this one here is there, but now we have the issue of fitting this in. And to do that, we're going to need project. Okay, I guess it didn't go anywhere. Did I dot? Project? Project? Am I in sketch mode? What is going on? Gaslit by Autodesk. Okay. Great. Great. What the heck is going on here? That's right. That's right. Lean into parkour. Parkour is such a beautiful, beautiful thing. Big fan. Always have been. Why is Fusion doing this? What is going on? Is this sketch not on the plane that I think it is? What's happening? Can I project other things? Can I project this? Okay, I think it's honestly just because it's a line, but that's never happened before, so I don't know. Let's see if there's another option. Parkour tag, you mean chase tag? Oh man, so we have played chase tag inside the chemistry building at U of M in the basement. That's always fun. We haven't done it in a couple years, but it is fun. I'm not very good at it. I think it's because I'm just too tall and like have trouble fitting under things, and a lot of people do really well when they fit through the small spaces. That's a struggle for me. That is a struggle for me. So all you short kings out there, huge advantage. Huge advantage. You should all do chase tag, honestly. You should all do chase tag. Yeah, it is fun though. And I think yeah, with the parkour guys here, we always, during the summer we'll play Ultimate Frisbee or sometimes like Capture the Flag. And sometimes we do this thing where there's just this like, we set up some cones and it's just like one chase tag drill that's just like chase somebody around this and try to catch them. And I was surprisingly good at that, which was surprising. It was surprising to me. I didn't expect myself to be good at that, but I got my hands on somebody a couple times. But some of them go down to Atlanta for, I guess, big chase tag tournaments, which I have yet to do, but maybe I'll do at some point. Oh, gosh. Project include. What are my options? Show me. Show me the options. That's all I want. Okay, I guess I don't get any options, so I'm going to have to re-show the capacitor and project that. CAD software, such a mystery to me. Please stop scrolling. Boom. Okay. Project this one. There we go. So that's the rectangle that I need to cut, which took me way too long to get. But this is the state of things. Because this is the rectangle that is going to allow me to push this capacitor into this part. And I also, can't forget about the frickin' wires, the leads on this thing. That's for sure. Okay, let's see here. Yes, it is. It is. You remember. It is going to be delivered to Zach. And he's been way more patient than he has any right to be. But it's just a fact that it was a much harder project than I anticipated. Is that a little bit embarrassing? Yup. But it is what it is, and I'm a man of my word, so I've been working on it, and it's gonna... This is really the push, This is really the moment where I'm like, okay, this is... I have done with this new design, like everything possible to make sure that it works. But if it doesn't work, then I just have to keep trying. That's just the nature of it. Okay, so that capacitor fits in right there. Nice, good, cool. However, got the leads that we got to account for as well. I'm going to do that after a bathroom break. So I'm going to be right back. Everybody, yes, I I understand that. It needs to be reliable enough for a Comic-Con. Yes, that's why it's so important to me, because he's going to be showing it to everybody. And I'll talk to you guys in just a second. Zach will have to have a few of the 9-volt rechargeable packs on him to replace. Honestly, I think I'm just gonna ship him this one. This is like barely dangerous. What's inside here is just a 3.7 volt. I don't think that's gonna cause any hubbub with the mail. So I'm just gonna give this to him, and there's USB-C charging built in. So essentially, we end up with a USB-C charge device, which is pretty cool. 52-second handstand. That's 610. That's pretty good. That's pretty good. I feel like my max is around a minute. At least it was. I think you should be very proud of that. Yeah, I mean, this device is going to Zach, but also the key here is that, like, the key here, one pack lasts the entire con, remains to be seen. So what's going on here? Let me do this quick calculation. Again, so if 13,000 milliwatt hours is to be believed, it's good that they say milliwatt hours. And the fact that they say milliwatt hours makes me believe that it's true. And that would mean that it's a 9-volt battery. So, 13,500 divided by 9, 1,500 milliamp hours. That seems really high. That seems really high. It even seems high for, yeah, it's just strange that they would say 13,000 milliwatt hours. It just seems high. But if it's true, that's 1.5 amp hours. And the motor that charges the launching draws about half an amp, which means that motor could load the spring for 3 hours, which seems like a lot. And then also, how long does the firing take? Probably 5 seconds. 5 seconds to load the spring, I believe. 5 or 6. So let's just say 3 hours is 3 times 180 times 60. 3 times 3,600 is a lot. 108,000. Yeah. 10,800 seconds that the battery lasts divided by 5. So just about 10,000 divided by 5 is 2,000. 2,000 firings. Like, it seems like too much, right? But that's what the math says. So if we put a safety factor of 10 on there, can do 200 firings. So maybe he can do 200. That also seems like a lot. I feel like it's going to be less than 200. But yeah, remains to be seen. And if he has a bunch of 9-volt batteries, that shouldn't really be a problem. They're easy to switch out, especially the way I'm building this thing. It does seem like too much, right? And yet the math is correct. So the question is, how is this 13,000 milliwatt hours? What is up with that? Yeah, exactly. I don't know how it is. I'll just check once it's built how many firings you could do. Honestly, and at this point, I don't trust what this battery says. It's kind of whack, but we will see. Because I have seen it before that these batteries list the capacity in milliamp hours, right, as you usually do. But they're not listing the 9-volt capacity. They're listing the original 3-volt capacity. But but now that they list them in milliwatt hours, which should be the same for 3 and 9 volts, it should be normalized by the voltage. Why is it still so high? That's just odd. That is just odd. But these maybe they're trying to fool people somehow. I don't know. We'll just have to see. Right, so the leads can be smushed down pretty flat, it looks like. And we really just need a little bit of space for them, because they can just kind of wrap around. Or rather, no, we probably want them to have a significant amount of space. And we'll probably solder wires to them. And yeah, Zach, he's got really, a great artistic eye. I think he can make something work. 10 millimeters. So we're gonna make a 10 millimeter. Hole, and we're gonna make this hole go like all the way back to here. And we don't need this to go into the cover because that's enough. So the battery wires are going to be coming from the top up here. I think I can get rid of the section analysis now. So there's going to be a battery wire here, one going into the button and one going into the capacitor. And is it because of the DIY tutorial you're saying that? Oh, asking about 610. It's literally silver door hinge shaped gadgets. Oh, yeah, that's a good question. The new brand new day web shooters, are they actually silver door hinges? That's a good question. Let's find out. It's crazy that there's already props and stuff. This world moves too fast. This is ridiculous. Why am I looking at shopping? I need to be looking at images. Hello? I need a picture from the movie set. Here we go. I feel like they didn't just use door hinges. That would be kind of crazy. They do look nice. I actually really like the look of them. I wish they wrapped around the whole wrist. It actually looks very similar to the size of this thing, Actually looks very similar to that. There's a DIY tutorial of how to make them out of door hinges. Interesting. Well, that's good. That's nice. Gosh, what the heck? Okay, so I need one wire. So one can come down from here, hit the capacitor, but then it has to keep on moving. Has to keep on moving somehow. So I think we're gonna need... Okay, this wire can move... I need to look at the capacitor again. This wire can go across the top of the capacitor, and that one can reach the lead really easily. This one can go along the bottom, that is true, but it can't reach except if I do something like this, I guess, right? Yeah, I'll just do this. That'll work. I can't believe we're going to fit this in. This is great. I don't want to speak too soon, but I'm optimistic. How many people do you think see my thumbnails and don't realize that I'm not making props? It's definitely my fault if they do, but it's just too bad for them, you know? Okay, there. Which direction are the leads going to face? So the leads are going to come out. I don't know why I'm gesturing towards the screen, like you can see where my hands are in relation to the screen. But essentially like coming out this way. And obviously they're going to be attached to the wires coming out of the battery and button and power button. And they're going to run, connect to wires that run under here, go to this input socket for the electronics module, and one more along the top, also connect to the input socket. In hindsight, this actually kind of fits perfectly. Like, I actually can't believe how well this ended up fitting. And it just fits right on in there. Okay. So that's the capacitor. Now, the resistor, I want to put a 1 ohm resistor in there because this battery, having regulation, doesn't have a very high internal resistance. And 1 ohm will do a little bit of damping, you know, give it a little extra protection. And it's not going to dissipate very much power because I think the most current we're going to be drawing is 0.5 amp. And that means the voltage drop across it will be 0.5 volt. And so at peak, we're going to get 8.5 volts at the motor side. And that should be enough. And it also further prevents over supplying the motor driver. Where? Great question. Great question. I do want to see something here. I want to see something here now. I'm also planning on putting a 100 nanofarad capacitor across each motor. That helps a little bit. It's not, you know, isn't going to do that much at the end of the day. But, and if we make this 1 ohm, we're just going to assume that this LiPo has no internal resistance. And we got a motor connected here. It might not necessarily have the same characteristics, but it at least shows what we've got. So what I'm doing here, the green line is the voltage across the capacitor, which should stay as close to 9 volts as possible. So you can see at the moment of pushing this motor on, it does dip a little bit. But I am honestly not sure if that's an artifact of the solver in this program or not. But also there's the voltage across the motor in yellow. And you can see that going between 0 and 8 volts. Now I'm honestly wondering if the motor has too much of a time constant. If I lower the capacitance across the motor, and it doesn't really help that much, I think. I don't know, does it? What if I take it away? What happens? No, nothing happens. Okay, so that capacitor isn't doing very much. I'm just going to put it there just, probably for safety. So let me just scroll back here. Yeah, it's only really dipping to like 8.5 volts, which I guess that's, you know what? I don't think it's an artifact. I think that's the current spike. There's a current spike when the motor turns on, and that drops the voltage across the capacitor. But at the same time, why would the capacitor voltage be able to drop like that? No, I feel like it's an artifact. It has to be an artifact of the solver. Yeah, I don't think that would physically happen. I don't think that would physically happen. Now, I do want to show what happens when I take this capacitor away and also wire this battery directly to the motor. Well, actually, I don't know if this would show it. Hold on a second. We're gonna see. We're gonna see. Okay. Yeah, we don't see anything. Okay. Hold on one second. What I meant to say was, so this is what we had before. Okay. La la la. Blah blah blah. And we press the button. I don't know why this is saying too much power. That's pretty dumb. Definitely not too much power. So this is what we had before, right? Yeah. Oh, now suddenly this is singing a different tune. This is odd. Maybe iCircuit that I downloaded in 2015 wasn't the best circuit solver out there. And of course I know that because, okay. So that capacitor is now charged. What's happening here? Oh, this is one, that's why it's a high time constant. I said 1 kilo ohm instead of 1 ohm. Got him. Okay. Here we go again. Great. This is our current circuit. This is the circuit I want to do. So I think the capacitor will go before sorry, I think the resistor will go before the capacitor. That's what I think. So ordinarily, batteries have some capacitance type impedance. So if I make this much smaller, like what it would actually be, I think like probably like 20 microfarads, I think. Watch what happens. Okay, I think it was actually even smaller. You see that ringing that happens, that voltage spike there? You see that? It happens across the capacitor. I know, right? The electronics ended up being a little bit more temperamental than I anticipated just because of the amount of torque that's involved here. I think it must have been even smaller, to be honest. If I make it... I'm not seeing the problem anymore. Maybe it was because it was a higher internal resistance. Quite odd. Quite odd indeed. Maybe it was something specific. I'm just trying to recreate the problem. I did have this working. I think you can kind of and you see these oscillations here, obviously. Now, I will say what I did have before, instead of this motor, because the motor in this is kind of just like whatever, you basically construct a motor with a resistor, internal resistance of 7.5 ohms, and an inductor. The inductor has 10 millihenries, and you have the you have to kind of generate a back EMF with the battery. So I'm just going to say back EMF of 3. Now, let's see here. So this is like as if the motor was spinning. The back EMF, that's why you have 3 volts across the motor, because the motor is spinning. And yeah, we still need to do what happened here. Okay, let's get rid of that. Okay. Voltage here. Okay. There. Now we're starting to see it. And I wonder, it's just like probably certain instances where, holy shit. That's across the motor. That's even worse. Of course, the motor would have stopped moving, right, by now, so there would be no back EMF. So it's not really realistic. I'm just trying to adjust for different back EMF levels. Yeah, I mean, so look, let's look at that voltage spike there. So this is what happens because you have dynamics of the peak is, it says like 9.2. But I feel like it must be heading over 10 volts to be generating the issues that I'm seeing. Like somehow, I don't know how. If I make this 20 micro, I was doing the simulation earlier and I saw like 9.7 volts. Yeah, let's check that out. 9.1. Okay, I need to get rid of this. Get rid of that. It's just kind of this high frequency behavior that I really want to get rid of. It's not going very high right now, but I'm wondering if I don't have the numbers right for the rest of the circuit that I was using before. We're going to recreate it. Okay, it looks like more capacitance actually increases this, so it's probably has something to do with the resonant frequency. That there's kind of a sweet spot and the battery does not satisfy it. See, that has less oscillations than, so we try 2 ohms, and let's try 50, pretty sure it's 50, right? There we go. Look at that massive spike. So it's not just about increasing the capacitance. Because if, let's see, increase this to 100. There, even more. 200. Holy cow. And now we're getting into the danger zone. feel like I've used, I think the Elvis board, is that the one you're using in mechatronics class? This sounds so familiar. I feel like that's standard. Oh, 300 farads. What am I doing? 300 microfarads. Of course it's still charging. Yeah, that's peaking above 10 volts. And so that would burn out the motor driver. This is the behavior that we don't want. And it looks like it gets worse as you increase this capacitance. This is why you got to be careful with your capacitance values, folks. This looks like it's improving. Oh, never mind. Kind of improving. So it's like 300 microfarads might be the peak, it looks like. And that could be like an internal battery capacitance. So I was going 2200. Sorry, not kilofarads, 2200 microfarads. Thank you. So now we don't have that peaking behavior anymore. We don't see it at all. This is why we're adding this capacitor. All right, 610. Thanks for stopping by. Hope to see you for some tutoring this semester. That would be a lot of fun. Just let me know if you need anything. Happy to help. Okay. So that resistor, 1 ohm resistor, might not be super necessary, but I don't know. I kind of want it. Like, what happens? What happens? Yeah, let's just find out. Let's get rid of that resistor. Look at this. What is this? Is this current? That's such a lie. Like, this is what I'm talking about when I talk about artifacts in this circuit solver. Why is it 10? I think it's because I connected it at a bad moment. Okay. What are you doing? Why is there current? Why is there 17 volts attached? What are you doing? Oh my gosh. So there's no way that there was 10 amps flowing back and forth through that. Okay. Yeah, it's just a mathematical artifact. That's so silly. That's where the resistor helped, of course, because it would dissipate that. That's why it's having trouble solving. So let's just look at the voltage here. We probably should just have a resistor anyway, because there is going to be some resistance, and we're just going to want to damp that out. Yeah, I think we're going to want to control that a little bit. So I'm going to put a resistor in real life. That's my call. That's my decision. We're going to put a resistor there in real life. And this has to be 2200 microfarads. What are you doing? Oh, again, we use 1 ohm instead of 1. Okay, 1 kilo ohm instead of 1 ohm. There we go. That's the behavior we want. Battery voltage will drop slightly, but not too much. Yeah. I hope I don't regret this. I hope I don't. But if the resistor ends up being too much damping, then I can just take it out. That's for sure. Okay, so in that case, we modeled this resistor as being in series with the capacitor. That is my goal here, in series with the capacitor. What is that vibrating? Okay. So let's see. got this resistor here, and I really just want to make like a slot for it. Okay, 2.5 millimeters in diameter. And in series with the capacitor. In series with the capacitor. So after the button, I suppose. Yeah, after the button, I guess. What's going on? I'm on airplane mode. This is ridiculous. All right. Maybe there's some emergency. Hopefully not. Probably not. Everything's probably fine. I'm just going to finish up this design, sign off, and deal with it. Okay, so where can I fit this resistor here? Tricky. Really tricky. It's true that it should go before the capacitor. That is absolutely true. It has to. Like, I really have enough space now that I could just stuff it in, but I really want to have space for it, like, on this side somehow. Let's just see what I can do here. Okay. So parallel to this axis. My mouth is still so dry from that blood donation. As soon as I log off, I'm going to get a big drink of water. How long is this resistor? About 7 millimeters. Less, but we'll count for 7. 2.5 over 2. 2.5 negative 2.5 over 2. Okay, so these two right here. Basically trying to make a slot for this resistor to basically just, you know, be the attachment point from the wire to the capacitor. So it just fits right in. Okay. I truly think that if I just extend this 5 millimeters, okay, we're done with the construction lines. Come on. Okay. Just gonna see. Just gonna see what happens here. Oh my God, of course. Somehow the construction lines returned. Okay, here we go. Negative 2.5. So that sends me out the other side for sure. Yes. However, we don't have to go that far because there. Now that looks like prime resistor real estate right there. It's a little bit too close to the corner. I'll fill it that. I will fill it that, and yeah, this will work. I do also want this to be able to be placed on the outside. So first things first. Goodness me, give me that section view back. I can't see shit. Okay. First things first, I'm gonna just extrude this out here so that the motor, or so that everything can be put inside easily. And then we're gonna fill it this, that, and one more, this. What happens? 1 millimeter. 1 millimeter looks good, but the more the merrier. 3, 2, 5, 2, 3, 2, 4. Okay, 1.24 it is. So that is our resistor spot. Goes right in there. And I'm going to fill it this too. There's nice enough space for the wire to go to the button. Okay. Okay. I think somehow we have done it, except we lost our screw hole on the cover. Is that going to matter at all? Good question. Good question. So there's 2 screws here. It's not the best. Not the best situation, but I mean, it's kind of fine. Like, there's really no reason to add any more screws. All I'm gonna do, and this might seem crazy, all I'm gonna do is add a slight deformation to make sure there's adequate pressure on the side where there are no screws. And how we're going to do that is this. 1 screw on every side should be enough. But 2 screws is really all you need to constrain the shape, isn't it? Listen, I'm going for 2 screws. That's what I'm going for. This is a difficult project, and there's no reason why I should try to have to find a spot for a 3rd screw right now when 2 screws is going to constrain this just fine. We're going to split the face first off with this line that I just drew. Split the face. Okay, then we are going to move the face. Hopefully this works. Sometimes it doesn't, and that would be really embarrassing. Take the face. There's the axis, and we're going to give it. Holy cow, what the hell are you? What the fuck? Okay, on second thought, we're going to extrude this to 0.15 millimeters. No, 0.2 millimeters. Tolerances by feel, everybody. Tolerances by feel. Then we're going to chamfer this edge. So also 0.2 and 2 distances. Now, is this illegal? Yes, but I'm doing it anyway. And so all we've got here is it's going to press slightly harder on this side, and we're going to get some deformation so that we get adequate kind of like, closing on this side, even though the screws are pressing here. And it's going to require a lot more force to deform this part outward because it's already going to be deformed. All right, that's our show, folks. Hope you enjoyed. Hope it was a pleasant experience. We are going to take one last look. We're gonna unisolate all. We're gonna show all bodies, and we're gonna show all components. No one would have known that we added a whole new circuit inside this thing. And we've got the mechanical module, the electrical module, and the battery module. And this is going to be one bad mother, that's for sure. Excited to build it. That's what I'm going to do right now. So thanks for watching, and I will see you guys very soon, I hope. Goodbye. Okay, how do I stop this thing? How do I turn this thing off?